Recording. I want to go through some of the main things that you want to make sure you have on this lab. I'm not going to go all the way through step by step. You know, this is the fourth lab that we've had now. We've had the bead lab, we had the ball on the floor, ball down the ramp, and now we have this conservation of energy. And, you know, we're starting to take the training wheels off. So some of this information you should be able to figure out. I mean, the background information, we talked a lot about that. You've done the POGIL, you have the skate park, so, excuse me, you can write quite a bit of information here. What I do want to get to is kind of trying to identify the independent, dependent variable. This lab is a little different from our other ones in that we're not just investigating one pattern, right? And so we're not just looking at one best fit line and so on and so forth. It's not really the pattern that we're investigating. It is the conservation of energy, the concept, the law that we're trying to investigate. So in that case, if you're not sure where to go or how to figure out what the independent variable is, dependent variable, especially because we were recording it, right? Or using the LabQuest 2 to record it, you can look at the research question. The research question should kind of give it away. We want to look at how the height of the ball affects its different energies, right? The key word here is affect. So how does this affect those? That makes this your independent variable and makes those your dependent variables. If all else fails, that's kind of the easiest way to go about doing it, right? We're still kind of looking at a relationship or connection. And just kind of looking at the way we design our graphs, you can kind of see what we're trying to get at. We're trying to get at what the height does to the different energies. Okay, so if you already have this written, fantastic. Okay, or you know, as long as what you have written is the gist of this, then we're good. So how about the constants? Things that you needed to make sure you had measured and written down. One of them is your motion detector offset. You need to make sure you had that written down. When we had you guys, you know, in the procedure, there was this part. I told you guys to read and do the procedure carefully. There was a part where you put the whiteboard a meter away from the books and then 0.8 meters away from the books and 0.5 meters. Every time you did that, you were supposed to write down what the actual measurement was from the, or what the reading was from the device. A lot of you guys just assume, oh, well, if you put it a meter away, then the reading's going to say a meter. That's not true, okay? Measurement devices, that's really an important part of science, is that we can only know as much as our devices tell us, our measuring devices tell us. And so we have to look at all our measuring devices with a grain of salt. Okay, so imagine, say, you're a doctor, right? And you look at an MRI scan or an X-ray scan or something like that, and you see a little blip. And you're like, oh, maybe that's cancer, or maybe that's a cyst, or maybe that's something, right? You have to interpret what the machine is telling you. And you have to kind of take your background knowledge and say, does it make sense for it to be cancer? Look at some other diagnostics. Look at all the information involved to determine, okay, well, there's no way it could be cancer. Maybe it's a cyst. Maybe it's a blood clot. Maybe it's, you know, there's all these different things that it could be. Right? So that's kind of what I'm talking about here is don't just take the numbers coming out of your machine and be like, oh, that's what it is. So when we do it over a couple positions, we then average it out and get a average offset. Generally speaking, now this is what I got from my data. I got something like 0.87, and this was like 0.3, or sorry, this was like 0.68, and this one was maybe about 0.37 or so. In other words, if you compare what it was supposed to be, if you actually measure it with a meter stick, and what the reading on the device was, you probably found that it was always short just a little bit. This is short about 13 centimeters or 0.13 meters. This is short about 12 centimeters. This is short about 13 centimeters. So they're all short by a certain amount. So when you average that all out, for me, okay, for my data, you should be doing what your offset said. But on average, my offset was about 0.127 meters. Okay, on average. Okay, on average. So you're going to need to use that. That's a constant. That is a, remember when we talk about precision and accuracy? It's precise in that if I included the offset, it's pretty close. It's repeatable, but it's inaccurate because, well, of the offset. In other words, it's not close to the real world value, but if I keep putting it at a meter, the measurement device keeps telling me 0.87. So the device is precise, it's repeatable, it will tell you the same thing every time, but what it's telling you is inaccurate. It's not, it's shifted. It's shifted. Think of it like a parking lot where they just repainted the lines. And you have one set of lines, and then you have the new set of lines, and they're like shifted. You know what I mean? All right. So you need to know that. You need to know the mass of the textbooks. If you used a textbook to put on top of your whiteboard, then you need to include the mass of that, and that was 1.9 kilograms. Pretty much all the textbooks are pretty much uniform. They're all 1.9 kilograms. And then the mass of the board that you use, that one you had to measure yourself. Okay, so whatever the mass of your board was, you should include that. Okay. For me, I think the big whiteboards, there were about 1.2 kilograms, but you really need to kind of measure that yourself. Okay. All right, make sure you include a diagram. Okay, your diagram is not just a picture, it's a picture that is labeled, right? A good diagram should label what is the important things you need to know. In this case, you're measuring how high it is, and then you're trying to figure out how fast it's going, right? Those are the things that you're trying to get. All right, so again, I'm not filling everything out. A lot of it is up to you. Use some critical thinking, discuss with each other, come to agreement. A lot of the first page, the data gathering stuff, I'm okay with you guys working together and having the same answer. Okay? That's the collaboration. It's not cheating. It's cheating when you're asked to come up with your own insight and you use someone else's. That's different. All right. So as far as the numbers go, okay, some students were confused about how to pick out the data, so I just want to review this one more time. So let me show you. Okay. So this is the graph that I had and the data that I had. A couple things that I did to this, I changed the scale. I changed the scale on the time, and I changed the scale on the energies, the position of velocities. I also changed it to dots. I think dots are nice. Dots make it very easy to see where I can pick out my range. So if I go from like 0.68 seconds to 0.92 seconds, here's my data on the right-hand side. These are the times. So the times help you figure out which dots to pick out. I want to pick out from 0.68 all the way to 0.92. Okay, so I'm going to go down to 0.68. Here's that time. Here's that time. But when I'm recording the height. I want to record the height, and I want to record the velocity. Okay, so for this time, this 0.68, I'll zoom in on this. Okay, for this 0.68 time, I want that position, and I want that velocity. Okay, these are the numbers that I actually want to record. Okay, this position gives me the height. Well, actually, it's almost there. There's something missing in this. These are the numbers that, again, the sensor is reading and telling us, and we already knew from calibrating earlier that they're offset. They're not right. They're short by a certain amount, right? So that means that when I actually go to write my 0.81 for my height, I need to make sure that I add back in the offset. So for this, remember remember to add your offset. Okay. So even though my reading on the sensor was 0.81, the real height is 0.937. Okay. If you're not sure where I got the 0.937 from, it's because I took the 0.81 and I added the 0.127. I added the offset back in. Right? So my real height is actually like 0.937. Now you don't have to show the original and the new and the real reading for every single entry. Just give me the real one. I just want this one. Right? I just want this one all the way down. But you need to add it back in for every single one. Okay. The velocity is fine. The velocity is not offset. The velocity is correctly calculated or measured, so you can use pretty much what it tells you right on the thing. So that from here, if you have this one and you have this one, then you can calculate your kinetic energy. Yep.
My group's offset was
1.67?
Yeah.
That's not right. So you'll have to go back. Go back and look at this. What did you guys actually record? And then you want the difference. The difference gives you your offset. The difference gives you your offset. So maybe you guys added instead of subtracted or something. I don't know. You already did everything? Well, that's unfortunate. Don't know what to tell you. You know what, though? I'll put it this way. If you feel frustrated about that mistake, that is the profession of being a scientist. Imagine the scientists and engineers who built the spaceship Columbia, and then it exploded and killed 6-7 astronauts. Imagine how they felt.
Dang, that sucks.
It's pretty bad. It's pretty bad. So it teaches you two things. First, when it comes to science, mistakes happen. Okay, mistakes happen. I mean, you can go all the way back. Imagine the Wright brothers. They didn't build that airplane the first time. They built it and they crashed. Then they built it and they crashed. And they built it and they crashed. That's the nature of science. It takes perseverance and it takes time. Actually, I'll tell you, last year we had a couple students go to the International Science and Engineering Fair. In what? No.
Oh, I know.
It was in Arizona, and they had a couple Nobel Prize speakers. Okay, Nobel Prize speakers, and one of them was a Nobel Prize in chemistry, and another was in biology, and every student there asked them the same question: what does it take to get a Nobel Prize in science? And they all said it just takes patience. It takes time. They didn't get their Nobel Prize the first year they graduated from college. They got it 20, 30, 40 years after working in the field, making mistakes and figuring things out over a long period of time. And it's not like each mistake will give you insight on where to go next. Sometimes mistakes just happen and you feel like you're in a dead end. But I think it's important to look at that and say, okay, well, change my perspective. Try something else. Approach it from a different perspective. Don't be disheartened. I mean, at least your mistake is not huge. You basically, it sounds like, David, that you're sighing because you just have to rewrite a bunch of numbers. At least you know what your mistake is, which isn't bad. Okay, so calculating kinetic energy, 1/2 mv squared, right? We've said before that you gotta make sure you square the velocity first. So as an example, I'll give what I have here and kind of walk through one calculation. So I'm gonna take 1/2 of my mass. In my case, for what me and the other physics teachers did, we had the mass of the board and the mass of the book. We put the book on top of the board, we dropped it. So it's the mass of the whole thing. We had 3.1 kilograms of stuff falling. So I'm going to take my 3.1 kilograms and I'm going to multiply by the square of my velocity. Okay. So when you're calculating this on a calculator, like I said before, you want to square it first. So I'm going to take my negative 1.717, okay, square it, and then multiply all the way through. So my kinetic energy here would be, it's kind of hard to see that decimal, but it's 4.57. If you end up with a negative kinetic energy, you messed up. Okay. Some calculators, you gotta be careful how you type it in. So look here. If I put 1.717 negative and I square it, I get 2.95 approximately, right? On the graphing calculators, if you put negative 1.717 and you square it like this, you'll see that it makes it negative. Because what it's doing is it's taking the negative and saying, oh, it's like, it's trying to do order of operations. It's squaring first and then applying the negative. So if you use a graphing calculator, you want to make sure you put it in parentheses and then square it. That way it's actually squaring the negative number. Otherwise, it's kind of putting the negative on the outside. So, in case you're using a graphic calculator or if you do it on a computer and so on and so forth, sometimes it'll misinterpret it. Okay, so you gotta have to understand what the calculator is doing. So, kinetic energy here, gravitational potential energy here, mgh. So I'm gonna do my mass times gravity times my height, which is going to be the 0.937, not the 0.81. And that gives me about 28.5. Or I guess you could do 28.47. You can do that too. Whatever. These are my numbers, right? You should be doing your own numbers. I'm just giving you an example calculation in case you get stuck. You're like, how do I do this? Blah, blah. Lastly, you add them together. You add them together. Yeah. For me, I got something like 33. I guess it'd be 33.04. If you want to go to the 10th place. Okay. Any questions about how to make these calculations? Or where to get your data from? Okay, so what I did, and I think it's kind of interesting to think about, I don't remember if I showed you guys this, but if you're looking at this 10 data points and you're like, oh, I don't want to do all these calculations, it's going to take forever. Well, we learned a very nifty tool last unit on how to make a bunch of calculations very quickly, right? That was Google Sheets. Did I show you guys this last time?
Yeah.
Okay, so I did. So here's all my the heights from the LabQuest 2, the real heights by adding my offset, the velocities from LabQuest 2, and then I just used the operation or the function, right? I create a function and I just boom have it calculate for me. So you got all the kinetic energy, gravitational potential energies. It may seem like it takes more time to do the first calculation, but it will save you significantly more time on the later calculations. So this is a good tool to use. So you're looking at total energies. I want to take a look at graphing just one of these. Okay, I want to look at total energy. So taking a look at my total energy versus height. Okay. When you plot your data, actually here, let me do a new one. I want you guys to see, I want to show you exactly what you will see. When you make a new sheet and you want to do height, okay, so we'll do height. Okay. And then we will do total energy. I'll just call this E total. Right? Okay. One thing that's kind of nice about Google Sheets, or not Google Sheets, graphical analysis and Google Sheets, I can just take the data and copy it over. So here's the heights. Copy, paste. Okay. And then I will take the total energies. Copy, paste. Okay. So if you look at the graph that you get, it might look a little curved. Okay, a little curved, right? You might be tempted to say it's quadratic. I think quadratic would be a pretty good fit. I think linear would be a pretty good fit too. But what I want to mention is that it can be a little deceptive because if you look at the axes only go down to 24. Okay? It's nice to zoom in when you're trying to extract data, but right now we're not trying to extract data. We're trying to get a big picture look. Okay, so instead of having it go to 24, I actually want to go to 0. Going to 0 is very useful for seeing the full kind of behavior. Right? So you zoom out, it really doesn't look that curved. You can use quadratic if you like. Quadratic can fit, linear can fit. You just have to understand or be able to explain why you use one over the other. What does it mean for this to be a linear graph? For it to be linear means that as the ball drops, as it's falling, you are losing energy at a constant rate. That's what it means, right? From here to here, you lose a certain amount of energy. From here to here, you lose a certain amount of energy. So that eventually you'll intercept somewhere over here, and you will have lost a certain fixed amount of energy. And it's linear. What would it mean to have a quadratic graph that curves like this, where it curves lower? For it to curve lower would imply that you don't lose energy at a constant rate as it falls. You lose energy at a faster rate as it falls. Does that make sense? Maybe. You can argue that too, because as something goes faster and faster, it tends to experience more drag. In case you're wondering about that, think of sticking your hand out the window. Do you feel like your hand gets pushed back more when you're going at 30 miles an hour or at 60 miles an hour?
60 miles.
Probably when you're going 60 miles an hour, you stick your hand out the window and it's like this, right? You feel the drag. You feel a lot. 90 miles an hour, stick your hand outside of an airplane. Right? There's a lot of drag, right? The faster you go, the more drag there is. The more drag there is, the more energy is being taken out of your system, right? So it's not unreasonable for this to be quadratic. You might actually lose energy at a faster rate. You can argue it either way. The important thing is that you argue it. Don't just put an equation there and just let it be. You have to understand what you're trying to write. All right, so use whichever equation. Maybe it's linear, maybe it's quadratic. And so then when you graph it out, again, you're going to have this line, whether it's curved or whatever, right? And then you're going to write your equations. Now for this one, you're doing all three graphs. You're doing kinetic energy, gravitational potential energy, and total energy. This is just a sketch. Okay, this is just a sketch. But your energies should look something along these lines. Your total energy should go downward to 0. And this is your gravitational potential energy. Your total energy will be decreasing, but not necessarily hit 0. And then your kinetic energy will be increasing this way to match this offset. Okay. Your energies should look something like this. Maybe not exactly, but when you sketch your best fit lines. And also, you may not actually get all the way to 0, right? Because your data was collected for only a certain range. So you might be only looking at like this part, right? But something along these lines. In other words, also, I want you guys to do this on your lines. Draw an arrow indicating the progression of time. Okay. What I mean is, this is supposed to be height. You start at a higher height and you are dropping. So time is actually marching this way. So notice that I draw my arrows to the left and not to the right. Because I start here and I end over here. I start here, I end down here. I start here, I end over here. Because it's falling. It starts from gravitational, turns into kinetic. So include the arrows. Include arrows. Okay? Now you get the equation. Yeah, you get this equation, this graph, so on. These ones I think you guys should be fine with. I think it's the triple graph that can be kind of confusing. You can't do a triple graph on graphical analysis manually, but you can hand draw it. So I'm asking for a hand-drawn triple graph. But if you're wondering about how to get the equation, you just have to do it on its own. This would be just total energy graph equation. Okay. All right. Last part on the 4th page. Look at the conclusion. Okay. There are multiple patterns that we're investigating. Okay, so how does kinetic energy change with height? How does gravitational potential energy change with height, and so on and so forth? First, you're going to decide whether it's linear, quadratic. That's what it means by the pattern. What kind of mathematical pattern fits it? Second, you're trying to decide whether it's increasing, decreasing, or not changing. And when I say increasing, decreasing, this is all with respect to height. So, in other words, I would say that although my total energy is decreasing with time, it is increasing with height. The higher I have it, the higher it is as it was falling, it hasn't lost as much energy yet. Or same thing with gravitational potential energy. The higher it is, the more energy it has. Whereas the higher it was, the slower it was, and so the less kinetic energy it had. Oh, sorry. So, I will repeat. Total energy with increasing height, increasing gravitational potential energy, decreasing kinetic energy. All right. So that's what you're trying to identify here. Now, if energy was totally conserved, right? If there was no energy transferring in or out of the system, what would the total energy graph look like? What was it supposed to look like? Can you say that in words, Vaughn? Just like that? Just like, should be like this, right?
It's a line.
It should be flat. Flat line. If there was no energy transferring in or out of the system, my total energy should have been flat. So in this case, it's not. And you can't dispute it. The data is indisputable. We lost energy as it fell. So what does that tell us? Is the law of conservation of energy supported or not supported? I'll leave it up to you on how you want to argue that. It really depends on what you count as part of your system. You should say something in the evidence here about whether, or at least in the scientific explanation too, about where that energy is going. Where is that energy going? How come our total energy decreased? Where did it go? Down to where? The ground. It hasn't hit the ground yet. Here's the ground. It's up here. From when I go from here to here, without having hit the ground yet, I have already lost energy. Where'd it go? Into the ground? It hasn't hit the ground yet. Into the what? Ground. In the air. The air gets in the way. The air gets that kinetic energy. That's how a fan works, right? You take a big board and you flap it at someone, you're blowing air at them, right? You are transferring kinetic energy from your board to kinetic energy in the air. And it's the same thing. The air has to get out of the way. That's what causes drag on airplanes. That's what causes drag on cars, on bicycles, whatever it is. The air is pushed out of the way, so you transfer kinetic energy from yourself into the air. So this energy loss, is going into the air. Okay, I think a lot of the rest of the stuff you guys should know how to answer it. Okay, so any questions about how to finish up the lab? This is due on Tuesday. Yes, David. The constants. Those are the constants. Now, the mass of the books you can write down, but the mass of the board you should have measured out yourself. You need to make sure you're using the data from your actual measurements. Same thing with the offset. Careful about just copying mine. It may not work for you. All right. Any other questions about the labs? So we do this lab to help give you some concrete, real-life experience measuring, working with energy. Hopefully this will help you with the test that's coming up on Tuesday so that you have some experience to be like, oh yeah, gravitational potential energy should be higher at the top, should decrease as it falls, and so on and so forth.